Hello everyone, this is Dr. Webb and welcome to the dramatic conclusion of our videos about the fundamental theorem of calculus. So in this one we're going to be talking about indefinite integrals and the fundamental theorem of calculus part 1. So in the last video we did the fundamental theorem of calculus part 2, and so this is the one that tells us how to evaluate definite integrals. And so if we have a continuous function little f of x from a to b, then to evaluate the definite integral of little f of x from a to b, what we need to do is we need to find an antiderivative for it. And so big F, its derivative is little f of x, and so this means that big F is an antiderivative of little f. And so to evaluate the definite integral for little f from a to b, we just take our antiderivative big F and we plug in b, we plug in a, and we subtract them from each other. Okay. Well, so we say this works for any antiderivative of little f. So what if we know two antiderivatives of little f? Both of these will work inside the fundamental theorem of calculus part 2. So what does this say about the relationship between the two of them? What can we say then about f of x and g of x? Well, if f of x and g of x are two functions that have the same derivative for all f, then what has to happen is they have to differ by some constant. There has to be some constant such that f of x is equal to g of x plus c for all values of x. So here's the theorem written out again. Why is this true? Okay, so let's start at the beginning. Let's let little f be the derivatives of big F and gf. And then let's just take some x value, any x value, call it a, and then we're going to set c, so this is going to end up being our constant, and c is just going to be the difference of f and g at a. So c is equal to f of a minus g of a. Well, then for any other b, we can get values for f of b and g of b involved by taking the integral from little f of x from a to b. Then the fundamental theorem of calculus tells us that that's going to equal, well, it works for any antiderivative. So it's going to be f of b, big F of b minus big F of a, but also it's going to equal big G of b minus big G of a. And so then if we rearrange this to, we've got f of b minus f of a equals g of b minus g of a. If we move f of a over, we can rearrange this to f of b is equal to g of b plus f of a minus g of a. Well, f of a minus g of a, we define that to be c. And so g of b plus c is equal to f of b, but also over here we can see that f of a is equal to g of a plus c. And so at a, they differ by c. And then this work with the fundamental theorem of calculus works for any other b, so they also have to differ by c at any other value of x. So f of b is always c more than g of b. Yeah, so f of b is equal to g of b plus c for all x values. Anything that we plug in for b. Okay, so this tells us that once we find one antiderivative for a function f of x, then now we know what all the antiderivatives look like. They are all, once we find the one big F of x, any other one is going to look like big F of x plus a constant. So this leads to what we call indefinite integrals. So if we have f of x as a Riemann integrable function, and we have that big F of x is an antiderivative of little f of x, then we define the indefinite integral of f of x. And so this is just the integral sign of f of x dx. Notice that there's no bounds here for this. So we're not integrating from between two places. We're just saying, this really is just asking what are the antiderivatives of little f of x. and it's equal to this big f of x plus c. So this c is really representing all the possible antiderivatives of f of x, right? And so this indefinite integral, it gives us the entire family of antiderivatives of f of x, because by the previous theorem, once we know that big f of x is 1, any other one is just going to be it plus a constant. Okay. And so this allows us now to take any derivative formula that we did earlier on in the course, and we can convert it then into an indefinite integral formula. So for example, one of these formulas that we've talked about is that if you take the derivative of sine, you end up with cosine. Well, how could we rearrange this into an indefinite integral formula? Well, so cosine is the derivative of sine, and that means that sine is the antiderivative of cosine. So if we take the indefinite integral of cosine x dx, then an antiderivative of it is sine. So the indefinite integral of cosine is sine of x plus c. And so this plus c here is to reflect that we're talking about all the antiderivatives of cosine of x. Okay, now we can talk about the fundamental theorem of calculus part 1. Okay, and this one is a little bit different than the fundamental theorem of calculus part 2. In the fundamental theorem of calculus part 2, we are trying to evaluate definite integrals. In the fundamental theorem of calculus part 1, we are trying to build antiderivatives of a function. So we're going to let f of x be a continuous function, and then we're going to just fix some x value a, and then we're going to define g of x to be what you would get if you evaluated f from a to x, right? And so since our variable x is up in this upper bound of our integral here, I can't use x as my variable of integration, and so we're going to change it. We're going to use t instead, because it'd just be very bad grammar if we're in the variable that we're integrating with is also one of the bounds of the integral. And so to avoid that, we just swap out our variable of integration. We use a different one. So we're using t here. Okay. So if we define g of x in this way, then it turns out that g of x is a differentiable function, and its derivative is f of x for all x values. So that means that g of x is an antiderivative of f of x. So notice that this g of x, it's being defined by this funky integral going from a to x of little f, right? And this funky integral, it's defining a function that's an antiderivative of little f. And so we can construct this antiderivative, g of x, and so then we can ask, now that we know that it is an antiderivative, which antiderivative is it? Well, if we plug a back into g, well, then we'd just be integrating from a to a of f of x dx. But if we're integrating just from a to a, if we're thinking about these definite integrals, really are talking about areas, but there's no width here. And so what's an area with no width? It has to be 0. So the antiderivative that we get out of this is the antiderivative such that we've set the value of g at the value that we started the integral with, a, to be 0. Okay, and this is going to be the only antiderivative of f of x with which this is true. Okay. So let's talk about why this is true. So we're trying to show that g of x is differentiable and equal to f of x. And so let's work on using the definition of derivative for g of x. So right here, we're thinking about the derivative of g of x, and that leads to this formula. Okay. Well, how is g of x defined? Well, it's an integral of f. And so if we want to evaluate g of x at x plus h, that means we got to move x plus h into our upper bound here. And then for g of x, it's up in our upper bound there. But then if we look at the numerator of this fraction, well, we're integrating the same function the same bottom bounds. They're both starting at A, but now they're changing at the top bound, right? And so it's sort of, you can think about it, we're taking the area from A to x plus h, but then we're subtracting off the area from A to x. So what would be left? Well, that would just be the area from x to x plus h. And so we can shorten it down to that, and I've pulled the dividing by h, I pulled it to a 1 over h out in front. And so this really is the limit that we want to get our hands on. What's going to happen to this as h goes to 0? Okay, so to get our hands on this, we're going to use a similar trick that we've seen before a lot recently. So since we're looking at this function f of t between x and x plus h, it's a continuous function, and so it has to have a maximum and minimum value there. So we're going to let big M sub h be the maximum value from x to x plus h, and little m of h be the minimum value on this interval. Okay, well, so since f of t is always less than or equal to m of h on the interval, that means that if I swap out f of t with m sub h, I'm going to get more area. I'm going to get a larger integral. Okay, and so that's where that inequality comes from. But now, in this integral, m sub h here, this is a constant. And so we're just integrating a constant here. And so what's the integral of a constant? Well, it's just going to be m sub h times the variable of integration. So that's t, and then evaluated at x plus h minus x. And so we write that out right here. And then you can see here, these x's cancel. And so we just have m sub h times h. So our integral from x to x plus h of f of t dt is going to be less than or equal to h times m sub h. Similarly, since f of t is greater than or equal to little m sub h, we can run through the same trick, but now we're going to be making our integral smaller. We're still integrating a constant, so this is still a constant. And so we can again use the fundamental theorem of calculus part 2 to evaluate this. I know that an antiderivative of just 1 is t. And so working out same as before, it's going to be little m sub h times h. And again, h, this is the distance between x and x plus h. Okay. So that work we have that the value of this integral is between h times the minimum value and less than or equal to h times the maximum value. So let's plug this into our limits. Well, remember we had a 1 over h out in front, so we have 1 over h times h mh. Well, the h and the 1 over h is going to cancel off there. It's also going to cancel off there. So what are we left with? Well, it's the limit of the minimum value on the interval is less than or equal to this value we're trying to get, and it's less than or equal to the limit of the maximum area. Well, now we're going to use the fact that our little f is continuous. So since f of x is continuous, as this interval gets smaller and smaller, all the values have to get closer together. And so that means, in particular, that means that the minimum value and the maximum value have to be getting closer and closer together as h goes to 0. And so, in fact, as h goes to 0, the minimum value and the maximum value, they both are going to converge at f of x. This is what it means for f of x to be continuous. Okay. So this means that by the squeeze theorem, since the integral that we want is in the middle and the outsides are both going to f of x, the squeeze theorem tells us that the middle is also going to f of x. So now let's put this together with everything that we had. So the derivative of g of x is equal to this. We're using the definition of derivative here, so it's g of x plus h minus g of x over h. We did work on that using the definition of what g is, big G is defined to be. We worked it down to this 1 over h times this integral of f of t. And then we worked out using the squeeze theorem what this integral equals, and it equals f of x. And so we're left at the end that the derivative of g of x equals little f of x. And that finishes the proof of the fundamental theorem of calculus part 1. Okay, so overall, at this point, we've talked about three types of integrals. So first we talked about definite integrals. And so this is what the fundamental theorem of calculus part 2 is telling us. And it says that if you're doing a definite integral, so this is where you're integrating a function between two bounds, what do you get out of this? Well, you get f of b minus f of a. So this is an actual value. And it's telling us something sort of about area, maybe. Or some, difference between the value of f from a to b. We also in this video talked about indefinite integrals. And so in indefinite integrals, you're just integrating a function. There's no bounds in it. You're just asking what are the antiderivatives of this function. And you end up with, you take one antiderivative, and then you think about adding any constant to it. And so for an indefinite integral, you're getting a family of antiderivatives. Any antiderivative is going to look like that. And then lastly, we had the fundamental theorem of calculus part 1, and this is where we define a single function based on this integral, where we put our variable in to one of the bounds, right? And so this is a single antiderivative of f of x. And what antiderivative is it? It's the antiderivative such that when you plug in a, you get 0. I know particularly the fundamental theorem of calculus part 1, where we're actually just defining a function based on an integral. This seems like a really funky concept. But it turns out that lots of times there's functions that really make the most sense to be defined by an integral. And so one thing that pops up in particular is often probability functions are best thought of as being defined by integrals. So if you go ahead and study something involving statistics or data science, you are likely to see functions defined by integrals when you're talking about probability. That is all for this video. I will see you again soon.